Hello everyone, we are Group 20. Today we are going to present our proposal, Image Inpainting with External Internal Learning and Monochromic Bottleneck. This is our outline. First, we will introduce the goal of our project. Next, we will present the text of image inpainting, and then we would introduce related work, which is including guided colorization and deep internal learning. Next, we would introduce proposed methods and our plans. Finally, we will show you our expected result. First, I will introduce the goal of our proposal. In this project, we want to implement the algorithm which is based on the paper image inpainting with external internal learning and monochromic bottleneck. And this algorithm can address the color issue in image inpainting. To be more specific, let's look at the bottom left picture. After inpainting, the result may appear somewhat unnatural. After implementing this algorithm, we will conduct additional redacted experiments to be more understand to this model. Next, we would incorporate extra modules to address issues with the original algorithm. Let's look at the bottom picture. In this case, it is hard for model to run color information of the impending part. Thus, the result of model would be weird. The color of two eyes would be inconsistent. Finally, we would utilize the whole model to address color issues in image manipulation. Look at the picture. We want to utilize the model to relate foreground color so that the foreground and background colors would match, and the whole image would be natural.
Image inpainting is a text that aims to complete the missing regions of an image with visually realistic and semantically consistent content. It can benefit general users in various practical applications, including unwanted object removal from an image, face defect removal, and image editing. There are generally two approaches to image inpainting. The first one is the learning-free method, and the second is using deep learning. Patch match is a learning-free method that utilizes the internal statistics of an image. It can generate smooth pattern and colors that are consistent with the non-missing part of the image. But the biggest drawback is that it often fails to fill in semantic-aware content. The deep learning method, such as gated conf, can learn semantic-aware model by training on large-scale datasets, but this method can suffer from color or texture artifacts. One of the most common artifacts that is observed from the deep learning method is called color bleeding. These methods trained on large-scale datasets tend to introduce inconsistent colors that do not conform to the color distribution of the test image. We can see that for these two in-painting image, they are unnatural pink color in the in-painting area. This is mainly caused by the color distribution gap between training and testing datasets. On the other hand, these kind of color bleeding artifacts seldom appear in the learning-free method.
Next, I would like to introduce some related work of our project. First, I'm going to introduce guided colorization. There are two kinds of guided colorization, user-guided and example-guided. The user-guided colorization focus on local inputs, for example, user strokes or color points. Color is propagated using low-level similarity metrics based on luminance, textures, and intrinsic distance. Colorization using optimization is an example of user-guided colorization. It's based on a simple concept. Neighboring pixels that have similar intensities should have similar colors. According to the user input in the left picture, the method colorized the image from the left to right. And another method is called real-time user-guided image colorization with learned deep priors. It is also a user-guided colorization method. It combines low-level cues along with high-level semantic similarities. It is a deep learning-based guided colorization method that learns semantic similarities from large datasets. This proposed method colorized a grayscale image, which is in the left, and guided by sparse user inputs, which is the second picture, providing the capability for generating multiple colorizations, which is the middle picture to the right picture. Next, I'm going to ex explain the example-based guided colorization. Example-based method get transferred color from single or multiple reference images to the target image. These approaches focus on finding the right correspondence between the reference and target image. Here is an example of using color transfer. Progressive color transfer with dense semantic correspondence. This method leverages semantically meaningful dense correspondences between images. Thus, it can achieve a more accurate object-to-object color transfer than other methods. Next, I'm going to introduce another part of our related work, deep internal learning. Training a deep convolutional neural network only on a single image has shown effectiveness in various image generation tests, such as super resolution or texture synthesis. The Deep Image Prior was the first project to utilize deep model as a prior to train image in painting. They have trained a deep model on the non-missing region of a single image from random Gaussian noise and try to propagate similar content information to the missing regions. And here are their results. Next, I'm going to introduce another part of deep internal learning, which is a method called internal GAN or InGAN. And InGAN is an image-specific GAN, which trains on a single input image and learns its internal distribution of patches. It is then able to synthesize new natural images of different sizes, shapes, and aspect ratios, all with the same internal patch distribution as the input image. While regular GAN train on a collection of images, and it generates new images from the same distribution. Internal GAN, however, train on a single image and generate new images from the same patch distribution of the input image. So next, I'm going to introduce the concept of external internal learning. As we have mentioned before, learning only from internal statistics is inappropriate, since external information is significant for content-aware image Inpainting. Instead of only using internal learning, external internal learning uses two neural networks. The first neural network learns the external knowledge by learning through massive datasets. And we can call the output of the first network as bottleneck. And we take the bottleneck as input of the second network. The second network then learns on the single image and try to get the internal distribution. And finally, we can get the output we want. So this is the external internal framework.
The method proposed by the paper we want to reproduce contains two stages. The first stage is external monochromic reconstruction trained on large-scale dataset for generating semantically correct content. The reconstruction net here can be any image Inpainting model that outputs a grayscale image. And the second stage is the internal color restoration on the grayscale image for propagating the color from non-missing parts using a progressive structure. There are two main advantages of this architecture. First, it is easier to train an Inpainting model for reconstructing grayscale image because the dimension is lower, leading to a more structure-preserving result. The second advantage is that the progressive network in stage 2 can gradually learn the color distribution of the masked area from the coarse to finer scale. The author conducted the experiment by using different image Inpainting model as the base reconstruction model in stage 1 and compare their result with the corresponding base model. For example, this column is the image generated by the original gated comp method, and the column next to it is using gated comp to generate monochromic image in stage 1, then apply stage 2 for color reconstruction. As we can see, no matter what the base model is, the qualitative result generated by their methods is better than the base model. This shows the effectiveness of their method, and it can be easily added after any Inpainting model.
This is our plan. We set deadline to each section. In following slide, I will focus on introduce experiment extend module section. Because we have meticulously introduced the method in previous slides. In experiment, we plan to conduct an ablation study to gain a deeper understanding of the algorithm. We will change the number of layers and see the impact of the number of layers on the performance. In extend module, we intend to implement a module with user-guided color functionality based on the idea provided in the author's future work. Here, I want to present the difficulties and uniqueness of our project. The difficulties of our project are to implement user guide color module. Because in the literature we refer to, the concept of user guided color was mentioned, but specific operational methods were not provided. Thus, we need to figure it out on our own. Here are the expected results. The following chart illustrates our objective and the corresponding expected result. We expect that the algorithm we implement have the same effect with the effect described on the literature, and the experiment result will be that with an increase in the number of layers, the photo quality improves, but the computational results required also escalates. The extra module can change the final output based on the guide. Finally, we expect the result of image manipulation is that the foreground won't appear abrupt against the background. This is our proposal. Thanks for listening.